Welcome back to another Code Meets World video, and this is a third quick video going back over the tree problems that I've done so far to show a better solution. So in the first video, I redid the invert binary tree problem with better code than I did the first time. Then I did the same thing with the maximum depth of a binary tree, and I wrote much better code for that one compared to how I originally wrote it. In fact, in my last video, I showed how you could do this problem with only 4 lines of code. So definitely check that out if you're interested. And also check that video out before you watch this video, because in this video, I'm going to use the updated code from my last video to show a much better solution to the diameter of a binary tree. So here's what I did. Link at the top here if you want to see the original video where I wrote this mess of code that you see on the screen. But just as a refresher, this problem is to find the diameter of a given binary tree, given the root node. And the diameter, as you see here, is the length of the longest path between any 2 nodes in the tree. So for instance, in this tree, it is 1, 2, 3, because the 4 node and the 3 node are 3 apart. The 5 node and the 3 node are also 1, 2, 3 apart. And it gets a bit more complex than this. You can watch my original video about the diameter of a binary tree if you're interested in seeing that. But here's the code that I wrote, and just as a refresher, it does work, but it's very complicated and entirely over complex. And so I'm going to simplify it a bit now. The first thing that we're going to do is make the function that calculates the depth simpler. And so in my last video, I talked about how you could do this in only 4 lines of code. So to recap that, if the root doesn't exist, the node that you pass in doesn't exist, then we can just return that the depth is 0. Otherwise, we can return the maximum of calling this function recursively on both the left and the right subtree. So like this, root.left, and then max depth helper root.right, and then we need to add 1 to all of this for each recursive call. So again, watch a previous video if you want to get all the info about how this works exactly. But basically, every time this function right here will calculate the maximum depth. So one side of any given node. So why do we need that? That's because the algorithm that we need to solve the diameter of a binary tree problem, what we have to do is we have to, for any node, we have to look at the maximum depth on the left, the maximum depth on the right, and then we add them together. And that's what I do in all of this code here. But we can write this in a much, much simpler way. So we can remove all this. We can just simply traverse the tree. So actually, I'm going to just honestly delete all of this. So the basic game plan is to traverse the entire tree, and for every node, check the depth of the left of it, check the depth of the right of it, add those together, and then I also need to keep track of like a global maximum. And just to show you what I did my first time, I actually passed in a maximum value through all of the recursive calls, and then every time I visited a node, I checked the maximum diameter of that node, and then if it was greater than this current max, I updated it, and then I passed that through all the recursion calls, and it got super complex. And what I wanted to do, what I really wanted to do is have some sort of global variable where I could keep track of it. And I did a little bit of digging and found out how we can do that. So if we make a function called init, this stands for initialization. And what this does is this will run as the first thing that our code does. And this is helpful because I can set global variables here. So I could say self dot max diameter equals 0, and then I can update this as I go, which means I don't need to do this crazy thing where I'm calling it in each of my recursion calls. So that's a way to simplify this problem. Another way is, now that I have this much better, so now that I have a much better depth function and a much better way to keep track of the maximum diameter that I see, this code becomes a lot simpler. So if root.left exists, I'm just going to do another post order. I'm going to turn this back into a post order traversal. So if the root.left exists, we just call post order traversal on root.left. And then we'll do the same thing for root.right. And then when we visit the node, because remember in a post order traversal, we explore both subtrees and then we visit the current node. When we visit this node, we can say that the node diameter equals, and remember the algorithm is basically add up the depth on the left plus the depth on the right. So we can just write that, and we can say max depth helper of left plus the max depth helper root.right. So we can simply use our helper function here that's a lot more efficient and find the diameter of whatever node that we're at in the tree. And then we just need to check if the diameter that we found for whatever node we're on is bigger than the maximum that we have ever seen. So we're basically going to iterate through every node in the tree and keep track of the max value. So then we can say that self dot max diameter is the maximum of whatever it is now, and whatever we found in this current calculation, like that. And then, of course, to make this actually work, we need to call post order traversal on the root, and then we just need to return self.max diameter at the end. So let me see if that is all going to work. Make sure I didn't make any typos or anything. Yeah. I think that's a typo. Max depth helper is not defined. Self.max. Oh, I think I know what the problem is. I think this has to go up a level. Sorry about that. Yeah. Perfect. So then let's submit that. Yeah, great. Okay, so the runtime of this isn't amazing by any means, but I was going for clarity of solution, and so I think this is a nice clean way to do it, and most importantly it makes a lot of sense. So hopefully that's helpful, and I will see you in the next video. Thanks so much.